So another application for first order linear differential equations is this mixture of brine problems. Brine is just a mixture of salt and water. All right. So the general outlay of the problem is that we have a solution going into a tank. This solution has a certain flow rate. Okay. This is the flow rate of the brine into the tank, say like 3 gallons per minute or whatever. And this brine, the brine that's going into the tank, has a certain concentration of salt, okay, in that brine. And so we have a flow rate of salt, not brine, but salt, a flow rate of salt into the tank of the flow rate of the brine into the tank times the concentration. Okay, that's how much salt in, say, pounds is going in. So separate between the flow rate of the brine going in and the flow rate of the salt in pounds going in. Okay? The flow rate of the brine is going to be like gallons per minute, and the flow rate of the salt is going to be in pounds per minute. This brine gets mixed into this tank and then comes out. Okay, and we have similar relation there for the flow rate of salt out of the tank. So let A of t be the amount of salt in weight in the tank at time t. Then we have the rate of change in the amount of salt in the tank is equal to the amount going in, okay, the salt per, say, pounds per minute going in minus the pounds per minute going out of the salt. Well, Rn, someone just tells you basically that, look, the flow rate of the brine, we're pumping this in at 3 gallons per minute, and we know that the concentration is, say, 3 pounds per gallon or whatever, and so we'll get a flow rate of the salt going in pounds per minute. Now, what about it coming out? Well, we have A of t is our amount of salt in the tank over the volume, okay? So that's what's going to give us the amount of salt going out, this R out, okay? And how you could basically get this is that you have R out is just generally given, and C out, well, what is the concentration? It's going to be A of t all over V of t. And this should have an R out, little R out over there. Okay, so V of t, the volume of the tank in general, is going to change with respect to time. All right, we can't guarantee that the amount flowing in is going to be equal to the amount flowing out. So I rewrite V of t here as V of t is equal to the initial volume plus this delta V of t term, the change, okay? This delta V could be positive or negative. You know, it could even change from positive to negative or negative to positive, depending on the change in the flow rate. So it could have a complicated relation. In general, if Rn and R out are constant, then we could write this delta V as Rn, the flow rate of the brine going in, minus the flow rate of the brine going out times T, okay? So if you're pumping in more than you're pumping out, but the amount is constant, then we just get this simple relation with respect to time, okay? And I write here, this is for, to go from this general form to here, you assume linear increase, okay? Which just basically means that Rn and R out are constant. All right, so we have an example here. Suppose a brine solution of salt, concentration 2 pounds per gallon. Okay, so that's the concentration flowing in. A well-mixed tank, so that we don't get sort of inhomogeneity in the tank for the concentration, at a rate of 3 gallons per minute. Okay, so the brine is flowing in at 3 gallons per minute, and that brine has a concentration of salt of 2 pounds per gallon. The tank initially has a volume of brine of 300 gallons. Okay? The brine in the tank flows out at a rate of 3 gallons per minute, so that's our lowercase r out. And something to notice real quick here is that lowercase rn is 3, lowercase r out is 3. Okay, so the volume is going to stay constant, as we'll see. If 50 pounds of salt were dissolved initially in the 300 gallons, okay, so we just have this tank initially with 300 gallons and we just dump 50 pounds of salt into it. Find the amount of salt after a long time. All right, so we just solved this problem with looking at our parameters here. Capital Rn is Rn times the concentration in, and we're given that in the problem. So the flow rate of the brine in is 3 gallons per minute. The concentration of that brine is 2 pounds per gallon, and we get that 6 pounds of salt are flowing into the tank every minute. VFT, the volume, is V naught plus delta V. Okay, and this is pretty straightforward because Rn and R out are the same. So you get the cancellation there, that's just 0. And we get a constant volume of 300 gallons. So there's always 300 gallons in the tank because the flow rate in of the brine is equal to the flow rate out. What about capital R out? Well, that's R out times the concentration coming out. And we have R out, it's 3 gallons per minute, but the concentration we don't have. Initially, we have the initial concentration. It's 50 pounds over 300 gallons. That's the initial. Okay, but that's going to be changing in time. Okay? That'll be changing in time, so you can't just assume that the initial concentration is going to stay fixed because you're pumping in a brine solution with a different concentration. And so we'll get this relation here, 3 gallons per minute for R out with this concentration, and 300 gallons is the volume, stays constant, and so you get AFT over 100 there. Okay, and we'll have then dA dt, writing this, summarizing all of this. We have Rn, we found that up here, 6 pounds per minute, minus AFT over 100. And notice that this whole term has pounds per minute, because you get a 1 over a minute here that I just omitted because AFT has pounds. Okay, so I didn't want to write here pounds per minute because technically AFT has a unit of pounds. Okay, so to just avoid confusion there, I didn't write it, but this has a 1 over minute there. Okay, and we could solve this through separation of variables. Here I chose to solve it with linear, just to kind of see something different. So it's a linear equation, and you just get the integrating factor. We have a video on how to solve linear equations and what the integrating factor is. And so using that procedure, we get E t over 100 for the integrating factor. And basically linear equation algorithm for solving these linear equations gives us this relation here. The right hand side here is 6 times, this is the integrating factor times 6. This is our quote f of x, right? if you put it in the standard form for linear equations. And so we integrate both sides. Integrating a derivative is straightforward. You just cancel, and then we have this integral on the right-hand side. And we get this constant of integration. Never forget the constant. It's actually really important for linear equations. And you end up getting this general form here. Well, we want to fix our C, our constant of integration. How do we do that? Well, we're told that the initial amount of salt is 50. And again, A is the amount of salt in pounds, not the concentration of salt. So we have 50 here, and that's at t equals 0. So we plug in, so we have two pieces of information again. One piece of information is the what's given in the problem, and the second piece of information is what we get when we plug in t equals 0 into our general form. We equate these two pieces of information and solve for C. We get that C is minus 550. And, after a really long time, that's just the limit as t goes to infinity. And so after a really long time, we get an amount of 600 pounds of salt in the tank. That's how much stays there. And notice 600 pounds over 300 gallons is 2 pounds per gallon, which is the initial concentration, okay? Which kind of makes sense that after a really long time, the tank concentration will be equal to the concentration of the brine flowing in, and we're seeing that. 600 pounds divided by 300 is 2 pounds per gallon. So let's look at another example, but this time having the volume change. Okay, so we're going to have a flow rate in that's greater than the flow rate out of the brine solution. So we're pumping out brine at 2 gallons per minute and pumping in at the same 3 gallons per minute that we had previously. Okay? So our volume now is going to change. That's the key difference. And you get V naught, the initial volume. This is going to be straightforward linear volume growth because the rates of flow in and out are constants. Okay? 3 minus 2 gallons per minute times T. Okay, so that's the rate of growth. This has a unit of gallons per minute there. Okay, so that the minutes would cancel and you just get gallons at the end. But I omit the units there to just avoid confusion with that. So here, what changes from the previous example is now we have 300 plus T at the bottom, okay? And keep in mind here that this 2 is coming from the 2 gallons per minute, okay? So just the volume here is what's different. All right, well, now we have the differential equation, and we could solve this differential equation using linear form. If you do that and you get the integrating factor and you fix the constant, you end up getting this. I omit the steps here, but this shows you then, of course, you also have to apply the initial condition A0 equals 50 because we're just playing off the previous example there. And we basically get this final form. And notice here that as t goes to infinity, this is the transient term, this goes to 0, but you get a consistent rate of growth for the amount of salt in pounds. Okay? And so you don't get that sort of asymptotic equilibrium solution that we saw in the previous example, which shouldn't surprise us because the first example is autonomous. And the second is not, because the right-hand side has this t there. Above, the right-hand side only had a. Okay, now of course it depends on t, but there's no explicit dependence on t. Here you do have this explicit dependence on t, and so the second example is not autonomous. We don't have that sort of same equilibrium solution that's just constant. And so the first example has an equilibrium solution, and it's a stable equilibrium. Okay, so if you start below or above that asymptotic amount of salt in the tank, then it'll go back to that asymptotic amount, okay? So it wants to go towards the amount of 600 pounds. Whereas here, we don't see that.